Today we're tackling the physics problem of finding out how long it takes a 1 kilogram mass to slide down a track in the shape of a quarter arc of a circle without friction, and then reach the bottom of the circular track. So how long it takes the mass to slide along this quarter arc of a circle and reach the bottom. We are assuming that the acceleration due to gravity is 9.8 meters per second squared, and the radius of the track is 2 meters. So before we tackle this specific problem in which the path we're sliding down is this purple circle, let's just think about tackling the more general problem of finding how long it takes an object to reach the ground when it slides along, an arbitrary track, any arbitrary path. Let's say that our track is the function y equals f of x, and the track starts at a height of y naught and ends at a distance of x naught. And so our mass is then sliding down this, arbitrary track in the shape of the function y equals f of x. What's the time to ground there? Well, in this case, let's set up an energy balance. So we know that the potential plus the kinetic energy is always equal to the potential plus the kinetic energy between 2 points. So let's see. So let's take this top point, for example. So what's the potential energy there? Well, that's going to be mg y naught, where m is the mass, g is acceleration due to gravity, and y naught is that starting height. We also know that the object starts from rest, so there's no kinetic energy, so k is 0. And then let's just take any arbitrary point along the path. So in that case, then, we're going to be at some arbitrary height y. So our potential energy will just be mgy. And then our kinetic energy will be at 1/2 mv squared, where v is the magnitude of the velocity vector. This mass is going to have some velocity vector at that point. And to find the kinetic energy, you have to take the length or the magnitude of the velocity vector and square it. So this is our energy balance for this arbitrary track. Let's cancel the masses. They all cancel. Divide every term by m. Then let's move this term over to the left side of the equation. So we get gy naught minus gy equals 1/2 v squared. Let's multiply both sides by 2. So we're going to get this equals the magnitude of the velocity squared. Okay, perfect. Now, let's also see if there's another way to represent the magnitude of the velocity squared. So let's imagine a vector. Let's call it r of t, which always points to the mass as it falls to the earth along the track. So this vector r of t, you plug in a time, and then out of that you get a length, which represents, the mass's length on the x-axis. That's going to be x of t. And then you get a height, which is going to be the mass's height above ground, y of t. And so you plug in a time, you get these 2 coordinates, and then those constitute a vector which point to the mass. So this is a position vector with respect to time that traces out the trajectory of the mass as it slides to the ground. However, we also know that y equals f of x. So here in our, let's actually make this equation vector slightly different. So y is actually f of x, but then x is also a function of time. So we get y is actually f of x of t. And then finally, let's now using this, let's copy that over here. Using this equation, our position vector, let's also now find our velocity vector, which is going to be the position vector differentiated with respect to time, differentiate each component with respect to time. This is going to give us dx dt, differentiate the top component with respect to time, and then using the chain rule on the y component here, this is going to give us df dx times dx dt. So this is the chain rule. This is our velocity vector. The magnitude of the velocity vector is, of course, also going to be the square root of the first component squared, so that's going to be dx dt squared, plus the second component all squared, so that's going to be df dx squared times dx dt squared. Okay, and then let's also just take a minute to square both sides here. So if I square this side of the equation, and then that gives me v squared, and then if I square this side of the equation, I get rid of that square root, and so now we have another representation of v squared here. So v squared is, let me also just factor out a dx dt squared from all terms, dx dt squared times 1 plus df dx squared. Okay, so now we have two representations of v squared. Let's combine them into one, where we find that, let's equate them. And so where we're going to find now that 2g y naught minus y equals this, dx dt squared 1 plus df dx squared. Also note again that y is just f of x. So let's put an f of x over there instead of y. It's a function. Our height is a function of our length because we're constrained to follow along a specific curve. So now let's also go through here and let's just isolate dx dt, and let's divide both sides of the equation by this. So we're going to get 2g y naught minus f of x divided by 1 plus df dx squared equals dx dt squared. And then let's also take the square root of both sides. So I'm just going to get dx dt and then square root on this side. I also just care, I don't care about plus or minus square root. I just care about the positive square root, because dx dt can't be negative. If dx dt has to be positive, which means x always has to be increasing with respect to time. And we see that, I mean, in all these curves, our x coordinate is always increasing with respect to time. We're always moving to the right. Same with the circular curve, because we're not really dealing with paths where the x coordinate would ever, decrease. We're never going to have paths, trajectories like this, where, we're moving to the, we're crazy trajectories like this, which can't even really happen in real life, where we're going to eventually be moving to the left ever. So that's not possible. X is always increasing, so we don't have to worry about the plus or minus over there. We just have to worry about the positive square root to keep dx dt positive. And now you'll notice that we have this, f of x is going to be a function of x, df dx is going to be a function of x. So this whole left side of the equation is just a huge function of x. Let's call that, big H of x. That's equal to dx dt. This is, nothing more than a differential equation. And moreover, it's a separable differential equation, because we can divide both sides by h of x, and then also we can multiply both sides by dt and bring, let me get rid of that, and just bring dt over here and separate our variables. So let's go ahead and do that. So if we do that, we're going to get dt equals, and then let's take the reciprocal of h of x, so that's actually going to be 1 plus df dx squared 2g y naught minus f of x dx. And then finally, let's integrate both sides now. If I integrate x from 0 to x naught, that's going to be, x naught, 0 to x naught, that's the whole trajectory. So therefore, time in that case is going to go from 0 to, let's call this capital T, the time of interest, the time it takes to reach the ground. So in this case, we're going to get big T, the time of interest, the time to ground, is going to be 0 to x naught, big square root, 1 plus df dx squared, 2g y naught minus f of x dx. So this equation, if you take any arbitrary path f of x, which starts at a height y naught and ends at a length x naught, then the time it takes for a mass to slide down that trajectory can be found by plugging f of x into this integral. You can solve for the time to ground here. So this is an important equation. And now let's just apply this equation to our problem, our specific problem. So here we have, let's just find, let's just find f of x here, because we're given this circular arc here as our trajectory, this purple circle. So let's find f of x and df dx, and just solve that integral then using those specific function, that specific path. So this is a circle obviously centered at the point 2, 2. This is our center here of the circle with radius 2, so 2 meters. So let's just go ahead and write the equation of a circle centered at 2, 2 with radius 2. This, hopefully everyone knows the equation of a circle. Let's isolate y. So we're going to get y minus 2 squared equals 4 minus x minus 2 squared. Take the square root of both sides. And then when you're thinking about if we want the positive or negative branch of the square root, well, I know that I want the negative branch actually, because the positive branch would give us this part of the circle, and I don't want that. I want this bottom half of the circle. So let's take the negative branch of the square root as we're finding the equation of the track, and then finally let's move the 2 over there. So get rid of that. And then, well, let me just get rid of this 2, move this y closer. So this is our equation for y, or in other words, this is the equation of the track, f of x, 2 minus, and then let's also just, let's, instead of writing that as a square root, let's put this as to the power of 1/2, because we also need to find df dx as we plug this into our, integral formula up here. So what's df dx? Well, the 2 goes away, bring down the 1/2, this is just the power rule. So, boom, here, everything's good. Decrease that by 1, and then a chain rule derivative of the interior, now that's just going to be negative 2 times x minus 2. Perfect. This negative 2 and that negative 1/2, those two things are going to cancel out perfectly. And so if we bring this negative 1/2 exponent thing to the denominator, we find out that df dx is going to be x minus 2 all over 4 minus x minus 2 squared. So I think that's right if I copied everything down correctly. And then, of course, f of x we also found out was going to be the 2 minus square root of 4 minus x minus 2 squared. I hope I also copied that down correctly. Okay, so we have that. We also know that x naught was 2 meters, y naught was 2 meters. That's just from, this problem. You can see 2 over here, 2 down there. Perfect. X naught, y naught. And then finally, g was 9.8 meters per second squared. So g, 9.8 meters per second squared. And yeah, those are all the components we need to solve this, to plug them into this integral. This integral cannot really be computed by hand. You just really need to approximate it using a Riemann sum. So you can plug it into Desmos as I have done just now. This purple curve, f of x, I'm trying to put my cursor over it right there. You can see it. This purple curve is the trajectory, the path. H of x is the derivative we just calculated. That's this blue curve here, which you can see is negative like that. And then because the curve slopes downwards. And then if I plug in, the derivative h of x up here and the path f of x down there, I plug in g, I plug in the x naught and y naught as 2 meters, we find that the integral approximates to 0.8375 seconds. So that's going to be our final answer for the time to ground. So the time to ground was 0.8375 seconds.